This is Jahan from National Institute of Technology, Andhra Pradesh from ECE department. In this, I'm going to talk about model predict control. Here, the model predict control strategy is a control strategy. Here, we will get the future state state of the system by using the present state and also the control inputs of the system. And here it is a feedback control strategy that considers the future behavior of the system in determining the control input at each time step. That is what I told. Here it's the block diagram of model predictive control. Like I took the example here. This is it's the feedback, and also this is the controller, like controller input. Here we'll get the input and it goes to the system, and it's the output or the state of the system. Next, we're going to talk about the terminologies. Here we have four popular terminologies, that is sampling time, time origin, prediction origin, control origin. Next, we are going to discuss the steps involved in MPC, the model predict control. Here, first we define the system model. Next, we formulate the control objective, choose a prediction origin, and choose a control origin, and we will optimize the problem and then apply the control inputs. That is, we are going to further discuss about the control inputs and update the model. Here I'm going to talk about the discrete time linear time invariant system. Here we define x of k plus 1, that is future, is equal to a into xk, that is present one, at kth instant, plus b into u of k, that is control input. Here x and u are the constraints set for the state and control inputs, which are usually represented by linear inequalities. That is, these are constraints. These are state variable, and this is control input. And A and B are the weighing matrix for system matrix, and also the B is for the input matrix, that is UK. Next, we are going to discuss about the objective function, that is we will call cost function, that is J is equal to this mathematical equation will be implemented by using the xk and uk. And here these are the weighing matrix used for relative weighing the state and control inputs, and to be chosen that this this thing is satisfied. And these are state and control sequence that we define, and this is linear time invariant system, and it is also called as constrained linear quadratic regulator problem. And here we going to uh, before we discussed about xk plus 1 is equal to a into xk plus b into uk, right? It's the same, but it's in matrix form. And here these are the weighing matrix of system state, and also this is for control input b. This is a matrix and this is b matrix. These are xk plus 1, that is the thing, and uk. And here we are discussing here about kth instant. Objective function is defined as like this, and these are constraint matrix constraint matrix. These are related to b, that is g into x is less than or equal to b constraint we have now. In that we will have g as this and b as this, and this for state variable, and this is for control input variable. These are the constraints we are defining. These are constructed from these. Next, we are going to, here we are going to combine the two, like state variable and control variable as one variable, that is decision variable. And we are going to we are going to define h, that is in terms of qx and ru. These are weighing matrix of input and state variable. These are constant function. These are constant function. For inequality is this, and equality is these two related. That is, that defines this. Objective function is defined as z transport into h into x. And here this is the control input you'll have. Next we are going to algorithm. Here algorithm in the means these are the steps we will see in MATLAB code. That is, first we define these a, b, and n of them and so on, and we initialize x naught and z naught for initial values, and we'll go on processing by using those base. And we construct ax, bu, and these weighing matrix from these a, b, and so on predefined, and we will go through the for loop, and we will get xk at kth instant and compute f equivalent and g equivalent. And by using those, we compute the z star, which is the decision vector that is we need, and uk u for control input, and we update z naught is equal to zk, and we go for the loop here, and go till nt minus 1 kth value is reached, and we'll solve the above problem by optimizing the above problem. Like we take the function that is f minimum con of f. These are defined values from these, like we'll limit the process, like boundaries, lower boundary and upper boundary for the z, by limiting the values of x and u here. And this is the MATLAB function which is going to compute the z values by giving the inputs this. Next, we are going to talk about the advantages and disadvantages. In this MPC system control strategy, we will have flexibility, robustness, constant handling, and performance optimization. We can optimize the performance of the system, and real-time implementation is possible. Next, disadvantages are computationally intensive. Like, this is matrix are so heavy that we can't compute like faster. It may not take, and model complexity will be more. And so complexity more means we'll have more errors and attenuations and tuning requirements. We have to tune such that the weighing matrix are portable with the xk and uk, so that will predict the uh, future state of the system by using them. Sensitivity to disturbance. This is so, like, attenuation is so possible in this. So we have to take care of this. In conclusion, like model predict control is a powerful strategy control that has found numerous applications in various industries. It is a prediction control terms that uses a mathematical model of the system to predict its future behavior and optimize control actions for a specified time horizon and control time horizon. Next, I am going to talk about the MATLAB code. In this, I'm going to discuss about the source code. That is, it is optimized using lower bound and upper bound. The optimizer problem. Here we predefine the values a, b, and n of t and q and so on up to z initial value. Like no, like zk we taken as xk and uk, like combination decision vector. And here for getting ax, bu, qx, and ru and h, we we wrote the code we write the code like this. so that we can compute these variables by using these predefined values. And by getting the above values, we can get like and we have to use the optimized code, right? Like f of, sorry, this screen is here. We going to like minimize the decision variable by using lower bound and upper bound of x and u. We will minimize those two by, and we are going by using those two, we will minimize the z, and we will the function we used is f minimum con, and here the function and xk will give the input and as well as the function, and it will give the output in z variable. And next here we will have the uk and xk, and here, and at last zk is equal to z. Next we'll the plot the graph for xk and uk, that is state variables and control input. This is the code for xk and uk, and I'm going to run. But like while I'm recording, it is not getting, so I'm going to show like this. If we run also, we'll get the same by using this code. That is these are the UK, and I'm using x of 1 and x of 2, two variables, xk as, and the uk as one variable, that is n is equal to n is equal to 2 and m is equal to 1, and I'm using, so I get this type of graph. You can use different values and you can see different types of graphs for your given input. Okay, thank you.